Hi guys, this is a recording for my tech memo for 6/30/10. Today I'll be showing how to set up an ultrasonic sensor, an HCSRO4 to be precise. It's a sensor that uses ultrasonic waves to determine the distance between itself and an object. How it does this is it measures the time it takes for the signal that is sent to come back. And using some math in the code, you figure out the distance. To set it up and connect it to the Raspberry Pi, you'll need a 1K ohm resistor and a 2K ohm resistor, as well as your sensor, a breadboard, and your Pi. Now, for the connections themselves, on your Pi, you'll find that you have various GPIO pins, each one with a different use. And you'll want to connect them the following way. So you're going to take your 5-volt power source and you're going to connect it to the positive terminal on your breadboard in any way that you'd like. And then you're going to take another cable from that same terminal and connect it to your VCC on your sensor. What this is going to do is just power up your resistor. It's actually how it's going to get to turn on and get the power that it needs to do so. Next, sorry, I'm trying to find a way to not make the cables jump across each other. Perfect. So then you're going to count your pins. So your pins are labeled 1, 2, if you can see, 3, 4, 5, 6, 7, 8, 9, and so on. And so you just want to find your ground pin, which is going to be your pin number 6. And you're going to plug that into the negative terminal of your breadboard. And take any other cable as well from the negative terminal and connect it to the ground node of your sensor. So now you've got your power and your ground. Now it's time to connect the actual sensor. Let me just clean up these wires so that they don't look as messy as they do right now, because it requires a little bit of work to make the circuit. So after that, you're going to take any of your GPIO pins. I'm going to choose number 33, and you're just going to plug it into any old random spot on the breadboard. After that, you're going to take your trig and connect your trig right on GPIO 31, since they're both regular GPIO pins. And that one can connect directly. Now, for the echo input, the echo actually only uses 3.3 volts. And since our power supply is 5 volts, we're going to need to drop down the voltage, and that's why we have the 2 resistors. So what you're going to do is you're going to take your echo and you're going to plug it in somewhere close to the one that we connected to pin 34, just a lone wire. And then you're going to take your 1K ohm resistor and connect it here. And let me see if I can rotate this. Sorry. So that it is not. Okay, it's going to connect there. So you're going to take your 1K ohm resistor and you're going to put it there. Actually, it doesn't make much sense to do that. And you're just going to connect your ohm resistor to that end. And then you're going to take the wire and you're going to put it on the other leg of the 1K ohm resistor. And then you'll take your 2K ohm resistor and you're going to want to flip it. I'm going to flip it 90 degrees and connect it from the same node, like the same train that the wire is in, and the ground. So, like so. And that's what your circuit should look like. I'll show you what mine looks like in real life and show you all the connections. All right, so this is the sensor that I have hooked up in real life. As you can see here, all of the connections are put on the sensor. This is our trig, which we plugged in directly into pin 31. And then this is the lone wire that we plugged into pin 33, just in the breadboard. As you can see here, we have our 1K ohm resistor. I actually have three 1K ohms, so I put these two in series. So that makes 2K ohms in total. We have here our ground and our VCC. This last resistor connects to the ground. And we can see the other connection goes into the yellow wire here, into the echo, which is the input. And ground and the voltage are connected. Alright guys, so here we have the actual code for the sensor to get it to detect and return you a distance value. So first what you're going to do is you're going to import the RPI GPIO library so that we can use the GPIO board on the Pi. We're going to import time because we're going to need to put some sleep commands in there. And then I'm going to use the GPIO board set mode, which just means that the pins on the GPIO board are numbered as they actually are. So like I said before, they'd go 1, 2, 3, 4, 5, 6, 7, 8, as opposed to like pin 16 being GPIO 24, which is the other mode that you can put in. I've set trig and echo to these two pins. You can do whichever ones you'd like, as long as it's easy for you to remember which ones they are, and you can do it fast, it doesn't matter. And then I put a print statement just to make sure that this is all good, and it starts the process. I set up my pins. Trig, remember, is the output. It's the actual one that sends out the signal. And then echo is the one that receives it and lets you know the distance. So echo would be an in, and trig is an out for the GPIOs. Then we're going to make a try and a while true loop. So while true, this is just going to go in an endless loop, just constantly checking the distance. You're going to set your trig to to off. That's why it says false. And you're just going to let it just settle so that there's no like previous measurements impeding it. There's no previous signals that are coming in that are going to mess it up. And you just want to do that for about 2 seconds, maybe one. I just want it to settle. Then for the sensor to actually begin working, you need to give it a little 10 microhertz pulse so that it actually just wakes up and then it knows like, hey, I should be expecting a pulse. So for that, you're going to just set the trig to true, sleep for, I don't even know how small this is of a second, and then set it to false again. Just so now it's got a little pulse and now it's waiting for the rest. Then you're going to make 2 while loops. While the input is 0, so there's no signals coming in, you're going to measure the start of the pulse using the time.time function, which just starts a timer for you to know, and we're going to use that later. And then the other while true loop is as soon as it goes to 1, you're going to end the timer for the pulse. Then you're going to take those 2 times and minus them from each other. So n minus start is the duration of it. And then you're going to use that duration and multiply it by this magic number, which is from physics calculation, which essentially just turns the speed of sound into a distance in centimeters. There's a whole thing of math that I could show you guys for that, but it's not very interesting. And all you need to know is you just always multiply it by this number, and it'll give you a distance in centimeters. I then take that distance, I round it to 2 decimal places, just for more exact measurements, and so that we don't get a string of 9. If you don't do this math, the pulse will just be a decimal value, which won't mean much to you, and it's really hard to calibrate like at a certain distance. If you want something to trigger in the system that you're making, it's really hard to know using that decimal point value. So you do this little math, turns it into a nice simple distance in centimeters. And then you just want to print out that distance. This will keep going. This will repeat every 2 seconds, approximately 2.000 something seconds. And it'll always print out the distance for you. Then at any point you want to stop it, you just press Control C on your computer and it'll begin. Let me move myself out of the way. It'll just say, hey, the measurements are done, and it'll clean up the GPIO ports to make sure that there's no old information on them until they're ready to be used again. And yeah, it's very simple code. This is pretty much a universal code for this. And it should work if you've set up your hardware properly and measure the distance for you, and you can use that in any way that you'd like. Thank you so much for watching.